So it's been a while since we've looked at this kind of stuff, but let's take a look at it now. Is the kind of growth represented in this account, is that direct variation? Is it linear growth?
What page is this?
It's on page 508. Is that direct variation? Is that linear growth? It's not direct variation, right? If it was direct variation, we'd expect what? We'd expect a straight line through the origin. So that's not looking so good. Cardell, what kind of relationship could I have here? It's not a linear relationship, is it? No? Yeah, exponential. Thank you. It's an exponential relationship. Now, one of the things they ask you to do, and I think it's kind of by way of reminder, is to look at the ratio of successive terms here. Look at this one divided by the previous one. This one divided by the previous one. Let's do that. See what happens. Now I've got those numbers here. Let me see if I can't make that even a little bit bigger. Let's jump up to 35 for the font. There we go. And what I want to look at is the ratio between this one and the previous one. So I'll do equals this one divided by this one. And I guess I got to make these numbers bigger as well. And there we go. 1.07. Let's try that again for this one divided by this one. Now, do I have to type that all over again? Well, let's just drag it down. In fact, let's drag it all the way down. And what do you notice? They're all the same. So to get from one term to the next, you're multiplying by this constant growth factor. And in this case, it's 1.07, meaning each one of these is 7% bigger than the previous one. So it looks like 7% is your rate of compounded interest. So that's nice. And Cardell was exactly right. This is exponential growth. All right. So what does your results say about the type of growth? This is exponential. Exponential. Nice. Find the relative rate of change in each year. That was 1.07. What can you conclude? Find the value after 10 years. Now, they're asking us to think a little bit beyond just, oh, let's keep on dragging this formula down. I can, but let's think about how you get from one term to the next. You keep on multiplying by 1.07, 1.07, 1.07. Now, if I want to get to the value in the fourth year, I'm going to take my beginning amount and multiply by 1.07 times 1.07 times 1.07 times 1.07. Is there a shortcut? Am I going to take my calculator out and multiply by 1.07 4 times? Or is there some shortcut that I could take, for instance? So if I wanted to find this in the fifth year, I could take 15,000 times 1.07 times 1.07. How many 1.07s do I need? So I probably should have chosen a smaller number here. Note to self. Yeah, it feels like there should be a better way to do this a little bit more efficiently. What is it? 15,000 times 1.07 to the fifth power. Okay, let's try that. Let's try that out and see if that works. So I'll do it here on my calculator. We'll start out with 15,000 times 1.07 raised to the fifth power. 21,038, and rounded to the nearest penny, so 28 cents. Nailed it. Wow. can you write a formula in general for this thing? Or what would I have to do if I wanted to figure out how much money I'd have in the 10th year? How could I write that? What expression would I use there? Scott? Trying to figure out an expression to calculate the amount of money I'll have in the 10th year.
It would be 15,000 times 1.07.
Nice. 15,000 times 1.07 to the 10th power. Nice. So let's do that. Let's just do that here. Now I'm going to cheat a little bit. If you hit the second key, then the enter key, it'll bring back your previous calculation. I'm just going to go up to the exponent and make that a 10. There you go. Now you got $29,507.27. So nice. 29,507.27. That's pretty outstanding. That's almost double what you started out with, right? In 10 years, you've about doubled your money. So if you can get 7% growth rate guaranteed, whew, jump on it. That's pretty good. That's really good. Let's see. Use your answer in question 3 to write an expression in the form y equals expression where the expression describes the amount of money after X years. We're starting with 15,000. So what's our expression going to be so that I can figure out the amount of money after X years?
Times 1.07.
Yeah, thank you, ladies. Times 1.07 to the x power. Nice. Let's check that that actually works. So we can do that on our sheets here. So let me pull open that, and I'll write in the formula equals 15,000 times 1.07 raised to this power. And there you go. So I can get any power that I want. There's another way that you could have done this if you want to just say, all right, well, let's refer to that one to begin with. We can lock that one. Let's practice that lock thing again. I can do y equals, and this term I want, let's see, y equals, no, I just got to do equals, my bad. Equals this times 1.07 raised to this power, but I want to lock that number in B1. Remember how we lock it? $sign here and a $sign there. That'll lock it. That way I always refer to that starting amount. Autofill, yes. The cool thing is then I could go back and say, you know what, I want to start with $20,000. And everything here updated nicely. Everything here stayed the same. So it's kind of nice if you can jump onto this. It's not something I'm going to require here. It's something that I'm letting you know. If you could do this on a test, it'd probably be extra credit. I'd be really thrilled if you could show me something like that on an exam.
Like, if you had one of the questions where it's like, write this as an Excel, like if we were to write it as like $1.
Yes.
Is that what you're talking about?
Yeah, so a lot of times I'll ask you to give me a formula that you can drag down. In this case, there's two different versions of the formula. One would be to start out, take your 15,000 times this. That's fine. The other one would be to start out with this and lock it, and then drag that formula down, multiplying by 1.07 to this power. So a couple different possibilities there for you, and I'll try and post this a link. In fact, it is already posted to D2L, so you can take a look at it there if you want to look back at it. It's not something I'm going to require. I mean, this course is, giving you exposure to Google Sheets and things like that. It's not requiring that stuff. All right. Now, in all the examples we worked with up till now, we've always had exponential growth. How about this example, the amount of coffee in your system? I get friends of mine that drink like a ton of coffee when we do our workouts on Monday, Wednesday, Fridays. I just don't know how their liver or kidneys can filter that stuff out before they go to bed. They just drink a ton. But is this growing? Is the amount of coffee in your system growing as a function of time? No, it's decaying. So exponential decay occurs in a lot of places, not the least of which is the number of days since we covered something in class and how much you remember, right? All right, a couple people smiling at that one. All right, but there's radioactive decay. Radioactive decay, has anyone heard of radiocarbon dating? All right, that's a way you can tell how old something is. If it at some point had some organic material, you can date it. But this is radioactive, or this is not radioactive, it's just decay. The amount of coffee you have in your system, or caffeine, over time is going to decay. So what you're going to do is figure out what's the decay constant. Now, how do we do that? How do we figure out the growth constant when we're dealing with our interest? How do I figure out, for instance, that you're multiplying by 1.07 when we had this data? Did we subtract? I don't think we subtracted. Because
You can find the scale factor.
yeah. So to find the scale factor, you're going to take this one divided by your previous one, and this one divided by your previous one. So I'll leave you to that for the group work here. You should see something similar to what we saw earlier. And then, try and complete some of these things as best you can. But let's get you in some groups and do some work.